In this video, we're going to explore the applications of modeling to a pendulum system, and not too surprisingly, we're going to discover a way to connect that back to the work we've already done with the spring mass system. But let's approach this as a pure modeling problem, where we have a mass at the end of a long rod or string, and when we look at the scenario and look at the forces that are involved, we have gravity pulling the mass straight downwards, and then there's also the force of the rod that's pulling back up on the same mass. What ends up happening is that the forces balance almost perfectly, except for a little component that is perpendicular to the rod, and that ends up accelerating the mass into a circular trajectory. So again, relatively simple system, only two forces in play, the force behind the rod or the string, and the force of gravity, and we're going to try to see what the mathematics predict about the length of the oscillations or the motion of the mass over time. Now, one challenge with this is modeling it correctly. Because this is rotational motion and not linear motion, we end up having to work with the torque version of F equals ma. And it's a little more complicated. You'll see this more in your physics class, so we won't go into the details here. But you can see that we have an acceleration, and we have the forces, the sum of the forces here, and we essentially have mass, only it's not mass, it's the moment of inertia that gets computed or used in this. The net resultant torque, which is what applies in the direction of the angle here, is mg sine of the angle from vertical. So we end up with mg sine of theta, but it's also moderated by, again, the length of this rod, because torques are affected by how far away from the center we are. Fortunately, when we start canceling things, we cancel an L, and we end up with m theta double prime. So we're going to divide through by m, and we'll divide by L as well. We do the same thing on the other side, divide by m and L. And then what we're left with is the theta double prime. And at m's cancel, g stays and is divided by L. And we just bring this over to the other side and it becomes positive. And we end up with an equation that looks very similar to ones we've seen before. We have the second derivative, or acceleration, plus g over L times sine of theta. This is actually a substantial problem in some sense, because this is a non-linear equation. We're running the angle in our system here through the sine function, but if we're willing to do a bit of a trade-off, there is an approximation that can make this a lot easier to work with, and that comes from, think of the sine graph, think of the linearization tangent line calculations we've done in the past. If we draw a tangent line to the sine graph, it has slope exactly 1, and this is our angle theta here, and this is sine of theta. You can very swiftly generate an approximation that sine theta is approximately equal to theta. It ends up being a line of slope 1 and intercept 0, so sine of theta can be well approximated with theta as long as the angle is small. And that's what we have to have here. Angle is small, or more specifically, close to 0, positive or negative. In practice, this means, less than 10 to 15 degrees. Okay. So in other words, if the swing of this pendulum is plus or minus 15 degrees in either direction, we can, to a high degree of precision, replace the sine theta with simply the angle itself. Well, making that approximation leaves us with this equation here, which is awfully similar to one that we've seen earlier. The second derivative plus, that was m, so it would be k over m, x equals 0. In fact, it's exactly the same equation, only instead of k's and m's, we have g's and l's, and instead of a position, we have an angle. So literally, the pendulum system for small angles is the same as the spring mass system. So how do we solve this? Well, we're going to solve it the same way we did before. We're going to assume that our theta now is equal to some exponential function, e to the lambda t. We're going to try to sub it into this equation, which means that we need the second derivative, but we might as well get there through the first derivative, e to the lambda t. So theta double prime is lambda squared, e to the lambda t, and then we sub that into the differential equation. When we do that, we have theta double prime, so let's be clear here, we're subbing into this equation here. We get lambda squared, e to the lambda t, plus g over L times lambda, sorry, times theta, these are thetas, times theta, which is e to the lambda t. There we go. Those have to consistently add up to 0. Hopefully you're seeing some patterns now. We're going to factor that out. Both terms have an e to the lambda t as a common factor. Make sure that looks as much like a lambda as we can get. And then we have lambda squared plus g over L equals 0. We can safely divide that by e to the lambda t on both sides. And that gets rid of that. We can do it because e to the lambda t is never 0. And we end up with lambda squared equals negative g over L, or lambda equals plus or minus the square root of g over L. Now there's a negative sign there. That would turn into a square root of -1 or an I value. So those are the lambda values we found. We go back to our solution form, which uses that lambda. So whatever our angle is as a function of time is going to equal e to the this over time. So we actually have two solutions, theta 1 of time, which is e to the negative square root g over Li times t, and theta 2 of time equals e, that's a g, e to the negative square root g over L times I times time. And again, we've seen this before, where we have an imaginary number in both sides, and it's plus and minus. Sorry, one of these should be positive. Let's take that, the positive one. And then we can build our solutions out of the cosine. Square root of g over L times t. Tidy this up. There we go. And theta 2 is equal to sine square root g over L times t. Again, the imaginary component here, we can expand that with Euler's formula, and by using appropriate constants in front of them, get rid of the I and get a purely real pair of solutions. And this is actually the kind of formula that Galileo would have created after tons of observations of pendulums and swinging masses on the end of ropes and on the end of rods to get the period. Because now we actually have enough information here. As a general solution, we just combine these two. If we look at the period of a pendulum, when it's only swinging a relatively small amount, so 10 or 15 degrees max, we can calculate the period, which is 2 pi divided by the coefficient inside. And that would be square root of L over G times 2 pi seconds. And notice how important the use of radians is here. We actually get 2 pi 6.28 whatever seconds as one of the building blocks for our formula. Square roots of G over L. This actually tells you what happens to a pendulum as you increase the length. If you double the length, you're going to get root 2 times the period. All of those kinds of unpredictable or hard to predict observations come from being able to model the physics of this, strictly F equals ma in the torque domain, and then allowing ourselves to use the complex numbers to build our solutions with complex exponentials. With that, we can gain completely new insights into the behavior of the system over time. We can predict much better what the system is going to do over time. And with that, that's actually the last video for the course. Just to let you know what's coming up next, at least on the math front in your first year engineering program. APSC 172 is the extension of what we've been doing in this course. It's going to work with multiple variables. You're going to have integrals of various kinds and derivatives of various kinds with more than one input variable. You're also going to get linear algebra, which is going to be the study of vectors, but in a whole other level, and you're going to again see connections from that to functions in ways you might not have expected. This whole C1 blah plus C2 whatever, that all comes from the study of linear algebra and abstract vector spaces. It might sound esoteric initially, but it is massively useful in terms of understanding how the mathematics is working here. And of course, you're going to see harmonic motion in a different light with APSC 112. And in second year, every single program has some course that's going to include differential equations in it, because again, The differential equation process or study is what lets us look at these kinds of systems, analyze the forces involved, and then use mathematics to predict what they're actually going to do. Without having to build them, without having to take any guesses, we know how this system is going to behave because we ended up with an equation that governed its behavior mathematically, and then we can work to solve it. So with that, we'll close and wish you all the success in your courses moving forward.